Welcome back. In this video, we're going to talk about converting non-deterministic finite automata into deterministic finite automata. Here again is our little diagram of the pipeline of a lexical analyzer, how one is constructed. So beginning with the lexical specification, we write our regular expressions. Last time we talked about this step, the conversion of regular expressions into non-deterministic finite automata. And this time we're going to talk about this step. And as you might guess, in the final video in this series, we'll talk about the final step, which is the implementation of DFAs. So here's the non-deterministic finite automaton we finished up with last time. And the first thing we're going to discuss today is an important idea called the epsilon closure of a state. And the basic idea of the epsilon closure is that I pick a state, and it could be a set of states, but we'll just do it for a single state. And then I look at all the states that I can reach by following only epsilon moves. And so B is the state that we're starting with, so B would be included in the set. And then there's an epsilon move to C, so C would be included in the set, and there's another epsilon move to D, so D would be included in the set. And so we would say the epsilon closure of B is equal to the set B, C, D. And let's do one more as an example. Let's take the epsilon closure of G. And when we switch colors, I'll do this one, I'll erase that and do this one in pink, or purplish pink. So the epsilon closure of G, well, we just have to follow all the epsilon transitions out of G. So H would be in the epsilon closure of G. But it's not just single epsilon moves. This is recursive. So any number of epsilon moves that I can take, all of those states are included in the epsilon closure of G. So in fact, I would also be included, A would be included, and B and C and D would also be included. And now, if I look at all of these states that have been colored in the light purple color, I can see that I can't reach any new states from those states using only epsilon moves. And so the epsilon closure of G would be equal to, and now let's write them all out here, it's A, B, C, D, G, H, I. Okay, so that is the epsilon closure of a state. Recall from the last video that an NFA may be in many states at any given point in time. That is, because of the choices it can make for a given input, an NFA may reach multiple different states. And the question we want to address now is how many different states can it be in? Well, if a non-deterministic automaton has n states and it winds up in some subset of those states S, how big can that subset be? Well, clearly the cardinality of that set has to be less than or equal to n. So the NFA can get into at most n different states. Now, if instead I want to know the number of different subsets. Well, how many different subsets are there of n things? Well, that means there are 2 to the n minus 1 possible subsets of n states. And there's something very interesting about this number. First of all, it's a very big number, so clearly the NFA can get into lots of different configurations, particularly one that has a lot of different states. But the important thing is that this is a finite set of possible configurations. And this is going to give us the seed of the idea for converting an NFA into a DFA, or deterministic automaton. Because all we have to be able to do to convert a non-deterministic automaton into a deterministic automaton is come up with a way for the deterministic automaton to simulate the behavior of the non-deterministic automaton. And the fact that the non-deterministic automaton can only get into a finite set of configurations, even if that set of configurations is very large, is exactly what we will exploit in the construction. Now we're ready to give the construction showing how to map an arbitrary non-deterministic finite automaton to an equivalent deterministic finite automaton. So let's begin by saying what's in our NFA. So we'll have a set of states, which we'll call S, and these are the states of the non-deterministic machine. There's a start state, little s, which is one of the states. and there's a set of final states, capital F. And then we also have to give the transition function, and I want to write out the state transition function. I want to use the state transition function to define a operator that we're going to find handy for defining our DFA. So let's say that A applied to a set of states. So X here is a set of states, and A is a character in the input language. So A of X is equal to those states Y, such that there is some X, little x here, a single state, in the set of states, such that there's a transition from X to Y on input A. Okay? So this is just a way of saying, of giving the transition function at the set level. It says for a given set of states X, show me all the states that you can reach on input A. All right? And then the other operation that we need is the epsilon closure operation that we defined a couple of slides ago. And I'm just going to abbreviate that as epsilon-CLOS, epsilon close. All right, so now we're ready to define our DFA. So what will the DFA be? Well, it's going to have all of these things. It's going to have a set. We're going to have to say what the states are, what the start state is, what the final states are, and what the transition function is. So let's begin with the set of states. The states will be the subsets of S. So the states of the DFA will be all possible subsets of the states of the NFA. So there'll be one state of the DFA for each possible subset of states of the NFA. And of course, this is potentially a very big number, but it's still finite. And so we can use that set of subsets of states as the state space of the deterministic machine. So now, what's the start state of the DFA? Well, that's going to be the epsilon closure of the start state of the non-deterministic machine. And if you think about it for a minute, this makes sense. What we want to do is we want to keep track of what set of states the non-deterministic machine can be in. And each state of the DFA corresponds to a different subset of states. So each individual state of the DFA tells us a particular set of states the NFA might be in. Well, which set of states might we be in at the beginning? Well, clearly the NFA starts in its own start state, but then before it reads any input, it can make epsilon moves. And so the actual set of states it could be in before it reads the first input symbol is exactly the epsilon closure of its start state. Now, what are the set of final states? Well, the set of final states will consist of those states X, and remember the states of the DFA are sets of states of the NFA, so that X is a set, and it's going to be every X such that X intersected with the set of final states of the NFA is not empty. So any state of the DFA that has at least one state of the NFA, one final state, excuse me, of the NFA in it is good enough as a final state for the DFA. Because remember, the goal of the NFA is just that it has some computation which accepts the input. It means there's some way to get to a final state. And so if any of the states is a final state, we're happy. And we can capture that here by just considering every state that has at least one final state of the non-deterministic machine as a final state of the DFA. And finally, we need to define the transition function. And how do we do that? Well, we need to say that for a given state X and another state Y, when is there a transition between them on some input A? Well, that there will be such a transition under what conditions? And well, let's write them out. So remember, we're in state X. And what do we need to know? Well, we need to know the set of states that we can reach on input A. And we just defined that. That's A of X. And then once we've gotten to one of these states, once we've seen where we can go from the set of states X on input A, there's also the possibility of making epsilon moves after that. So furthermore, we have to take the epsilon closure of that set of states. Okay? And so we'll say that there is a transition from X to Y if Y is equal to this set of states. All right? And notice that there's only one such set of states for any x, and that guarantees that this is a deterministic machine. Each state will only have one possible move on each input. So we can just now go through our checklist and see if we have a deterministic machine. We have a finite set of states, we have a start state, we have a set of final states, and we have a transition function with only one move per input and no epsilon moves. And so that is, in fact, a deterministic machine. And the property that it maintains is that each step of the computation, the state of the DFA records the set of possible states that the NFA could have gotten into on the same input. So let's work through an example of constructing a deterministic machine from a non-deterministic machine. Here's the non-deterministic finite automaton that we built in the last video, and again, this is the one I used at the beginning of the video to define epsilon closure. So we're going to do the example slightly differently than the construction I gave on the previous slide. If we actually had to write out all the subsets of this many states, it would take us a very, very long time. And it turns out that not all of the subsets are actually used by the DFA. So we're just going to enumerate the states that we actually need, and we'll do that by beginning with the start state of the DFA and then working out which additional states are required. So how do we do that? Well, we begin with the start state of the NFA, which is just this state A. And then recall the start state of the DFA is the epsilon closure of that state. So that corresponds to this purple set here. All right? So the first state of the DFA, the start state, is the subset of states A, B, C, D, H, I. And now we have to work out from this particular state, from the start state, what happens on each of the possible input values. So the alphabet of this machine is 1 and 0, so we have to have two transitions out of this state, one for an input of 1 and one for an input of 0. So let's do input 0 first. And we can see, looking at the purple set, that there's only one possible transition, and that's from the state D to the state F. Right? So certainly the state F is included in the set of states that the NFA can reach, but then once we get to state F, there's a lot of epsilon moves that we could take. And so in fact, the second state of the DFA corresponds to a much larger set. It's the epsilon closure of F. And that is this set of states, F, G, H, I, A, B, C, and D. Okay, so this is the set of possible states that the NFA could be in after reading a single 0. Next, let's consider what happens from the start state on an input of 1. Which possible states can the NFA reach? And if we look at the transition function, we see there are two possible moves that the NFA could take. It could be in state C, in which case it would move to state E, or it could have been in state I, that's also part of the purple set, in which case it would move to state J. So there are two possible states that the NFA can get into as a result of reading a 1. And then after that, there's a bunch of epsilon moves that can take place. And in fact, it turns out that after reading a 1, the machine could be in any state except for state F. And that's this set of states. And you'll notice that this particular set of states, the red set, includes the final state of the NFA. So this is also a final state, indicating that after reading a 1, the NFA could be in an accepting state. And so this will be an accepting state of the DFA. Well, we still have to fill in for both of the two states that we've added here, the two states on the right of the machine, what they do on input 0 and what they do on input 1. So let's figure that out. So beginning with the red state, on input 0, what can happen? Well, look, the red state includes state D, and it can move to state F, but we've already computed what happens on the what the epsilon closure of F is. That's just the green state. And so if I'm in the red state and I read a 0, I move to the green state. If I'm in the red state and I read a 1, you'll see that both states, NFA states C and I, are in the red set, and so it just takes us back to the red set. And similarly for the green state, if I read a 1, I move to the red state, and if I read a 0, I stay in the green state. And so this then is our deterministic machine. Down here, this is the deterministic machine, and again, it simulates the NFA. So on every move of the deterministic machine, it records the set of possible states that the NFA could be in, and it will accept a string if and only if the NFA could accept the string.